Hey, I want to talk about a very useful and very powerful integration technique known as substitution. Let's consider the integral of 5x to the fourth times x to the fifth plus 10 all to the 14th with respect to x. This would be very unpleasant to expand algebraically so that you could do it with the techniques that you already know, and so we need a new technique. And that new technique is to create a new variable. I'll call it r, and I'll set r equal to x to the fifth plus 10. Now, how I chose the x to the fifth plus 10 is an important and interesting question that we'll discuss some more. Choosing the variable r is also a little bit unusual. Most of the rest of the world tends to use the letter u here, so much so that you will often hear this technique referred to as u substitution. U is perhaps the worst possible choice of letter here, and so I don't use it. And the main reason is that the very next technique we're going to use is called integration by parts, always taught in terms of the variables u and v, and the u in integration by parts has absolutely nothing to do with the letter that you choose for substitution. There's no substitution going on there, and this confuses students. And so you can pick any letter you like there. Probably shouldn't pick X. D is also a bad choice, but I'm partial to R. So we're going to let R equal x to the fifth plus 10, so that the derivative dr dx is 5x to the fourth, or in differential notation, dr is equal to 5x to the fourth dx. And the beauty here is that this lets us entirely rewrite our original integral in terms of the new variable. In particular, the x to the fifth plus 10 is r, and so we have the integral of r to the 14th, and then the 5x to the fourth times dx. Well, 5x to the fourth times dx is just dr, and so that gives us dr. And that's a very easy integral to compute. You get 1/15 r to the 15th plus a constant. Of course, I can't ask you what the integral of 5x to the fourth times x to the fifth plus 10 to the 14th with respect to x is, and have you answer 1/15 r to the 15th plus a constant. There were no r's in the problem. We made up the variable r. And so we have to turn the r back into something in terms of x in order to actually finish answering the question. And since r is equal to x to the fifth plus 10, this becomes 1/15 x to the fifth plus 10 to the 15th plus a constant. And like you can always do with indefinite integrals, it's very easy to check your work, take the derivative of the answer here, and see that you'll get 5x to the fourth times x to the fifth plus 10 all to the 14th. Don't forget to use the chain rule, and you may as well take a moment, check your work, and see that we got it right. We did. Now, suppose instead that for the same problem, we had chosen r equal to 5x to the fourth instead of x to the fifth plus 10, a perfectly reasonable choice. We would then find in differential notation that dr is 20x cubed dx. And while we have our r right here, our 5x to the fourth, that's r, what are we going to do about the 20x cubed dx? We need some way to write dr. How are we going to deal with that? And also, what are we going to do about x to the fifth plus 10 all to the 14th? How are we going to get that out of our new variable r here? There just isn't a way. And so the choice of r equals 5x to the fourth doesn't help us solve the problem. It's a bad choice. We would have to start over. And how do you start over? You start over like this. This substitution will actually let us rewrite the entire integral in terms of the new variable, which will always be the goal in a substitution problem. Which is to say, substitution is always about good guesses. How do you decide what to guess? Well, the answer is you do lots and lots and lots of substitution problems, and you just get better at doing them through practice. So here are a few to try. Take a few moments, try each of these. Give you a little hint for the first one. You should set r equal to 3x squared. That's a good place to start. Turns out there's more than one way to do this one, but this is the most straightforward and simplest way. Okay, take a few minutes, do these, pause the video. We will do them one at a time. So when you unpause the video, we'll do the first one, then I'll give you another chance and maybe a hint on what to substitute for the second one, and same for the third. So when you're ready, start her up again. See you in a minute. For this first one, if r is 3x squared, then dr is 6x dx. And the e to the 3x squared is just e to the r. And 6x dx is dr. And so we've rewritten the entire integral in terms of the new variable. And that's a nice easy integral. The integral of e to the r dr is just e to the r plus a constant. And r is 3x squared. And so our answer is e to the 3x squared plus a constant. If you need a little help with where to start on this second one, start by setting your variable equal to x squared plus 1 and go from there. Since r is x squared plus 1, the derivative of r is 2x, so dr dx is 2x, or in differential notation, dr is 2x dx. And so we can rewrite the original integral in terms of the new variable as the integral of the square root of r dr, where here's our r, x squared plus 1, and the dr, 2x dx, that's dr. So that's how we got the integral of the square root of r dr. It's easier to do calculus if you rewrite the radical in terms of a rational exponent. The square root of r is r to the 1/2. And now you can apply the usual power rule. You add 1 to the exponent, divide by what you come up with, which gives us r to the 3/2 divided by 3/2 plus a constant. And dividing by 3/2 is the same thing as multiplying by 2/3. And so finally we get 2/3 times x squared plus 1 to the 3/2 plus a constant. And for the last one, let your variable r equal the natural log of x, so that dr is 1 over x dx. It helps to notice that by basic algebra, natural log of x over x is the same thing as the natural log of x times 1 over x. And that makes it clear how this substitution is going to allow us to rewrite that integral. In particular, it becomes the integral of r dr. The natural log of x is the r. 1 over x dx, which is all that's left, is the dr. And that's a nice easy integral. You get 1/2 r squared plus a constant, or 1/2 the natural log of x all squared plus a constant. Up until now, the integrals that we've been looking at have been very carefully chosen to work out just so. I want to show you one quick example of one that takes just a tiny bit more work, give you the chance to try 1 or 2 of them, and then I'll set you loose on your homework. Let's give it a shot. Let's consider this integral, the integral of x squared over x cubed plus 4 with respect to x. I'll let my new variable be called u this time, just so that you can see it done that way every now and then. So we're going to set u equal to x cubed plus 4, which gives us that du is 3x squared dx. And there's where the fun begins, because we don't have a 3x squared dx in the original integral, although we do have an x squared dx. And so the trick here is multiply both sides by 1/3 or divide both sides by 3, however you like to think about it. And you see that 1/3 du is equal to x squared dx. And that lets us rewrite the original integral entirely in terms of the new variable. We start with the integral of 1 over u. That's the 1 over x cubed plus 4. What's left is x squared dx. And x squared dx is just equal to 1/3 du. This is all multiplication. We have 1 over u times 1/3 times du. 1/3 is just a constant, so we can pull it outside of the integral, like so. And I will often skip that step beforehand where I've got the 1/3 awkwardly wrapped up inside the integral there, and just go straight from this step here where we've got 1/3 du equals x squared dx to that step right there where I rewrite the integral as 1/3 the integral of 1 over u du. That's an easy integral to do. It's 1/3 the natural log of the absolute value of u plus a constant, or rewriting the answer in terms of the variable x, we get 1/3 the natural log of the absolute value of x cubed plus 4 plus a constant. And again, you can check your answer by taking the derivative. You'll find that you get x squared over x cubed plus 4. Okay, take a minute or two, give these two integrals here a try. When you've got them done and you're ready, start the video again, so pause it now, and then we will go through them very quickly in just a moment. Here we let r equal x to the 4th plus 1, so dr is 4x cubed dx. We don't have a 4x cubed dx, but we do have x cubed dx. Divide both sides by 4, or multiply both sides by 1/4, to get 1/4 dr is equal to x cubed dx. That lets us rewrite the integral as the integral of r to the 10th, that's the x plus 4, x to the 4th plus 1 to the 10th, and then the x cubed dx is 1/4 dr, and you can see I pulled the 1/4 outside the integral right from the start. And that's a nice easy integral. The integral of r to the 10th is 1/11 r to the 11th. You can multiply the constants. 1/4 times 1/11 is 1/44, and you end up with 1/44 x to the 4th plus 1 to the 11th plus a constant. Moving on to the next one, let your new variable r equal 7x, and if you didn't think of that, then pause the video here and take a moment and see if you can finish this one. Since r is 7x, dr dx is just 7, or in differential notation, dr is 7 dx. And dividing both sides by 7, we get that 1/7 dr is equal to dx. And that lets us rewrite the original integral. The integral of e to the 7x dx becomes the integral of e to the r, and then the dx becomes 1/7 dr. So I've pulled the 1/7 out in front, and I've written 1/7 the integral of e to the r dr, which is a nice easy integral. You get 1/7 e to the r plus a constant, and since r is 7x, you get 1/7 e to the 7x plus a constant. Okay, substitution, a great and powerful technique. It's like the Wizard of Oz of integration techniques. So you need a lot of practice. There's a homework with lots of substitution problems to do. Go to it, have some fun. See you soon.